Welcome everyone. Yeah, so we wait for people to join us and then we can start. We can start. Okay, yeah, so we said we'd be doing physics today. Okay, I just didn't state what topic, so direct current circuits. All right. Good evening, everyone. Dismas, good evening. Nonde, good evening. All right, we are set to start. So, direct current circuits. So when we have 45 viewing, we will start to take which do know. So when we finish doing direct current circuits, since we've done a little bit of rotational motion, then we can do oscillations. Okay, so just three more people, and then we start. Anyway, looks like people could be asleep or they'll join us later. All right, so direct current circuits. The main formulas, the main equations to know here are the main things to know. Number one, you need to know the appropriate equations. Number two, you need to know Kirchhoff's laws. Okay. Number three, you may need to know something about resistivity. Number four, you may need to know something about internal resistance. Okay. So once you know these, at least you're set for any basic question that they may set for you. So the equations, and the main equation that we're going to use for now, rather the main equations are V is equal to IR, okay, P is equal to I squared R, or P is equal to IV. P is equal to IV, okay. So I remember V is equal to IR by writing the word virus, because if you put US, this reads as virus. I remember P is equal to IV by remembering VIP. Then it is because what FFE. Then Kirchhoff's laws, there are two laws that we're going to talk about. We're going to talk about the junction law and we're going to talk about the loop law. Sometimes some people call it a rule, some people call it a law. I don't know. Then resistivity, just the equation, R is equal to rho L over A, and so on. Okay. Internal resistance, giving us we'll have this equation when I show you what one of the questions that we are going to do. Okay, so internal resistance, E is equal to I R plus R. Okay, so these are the main things that you guys are supposed to know. We'll try and talk about each of these things, maybe except resistivity, but to talk about 1, 2, and 4 in this session, so that at least you guys have a little bit of confidence. Okay, so we'll start. I think we're going to go straight to the use of Kirchhoff's laws, and then you're going to see us applying these equations under these laws. All right. So, Kirchhoff's laws. Kirchhoff's laws. Basically, there are two laws. Number one, the first one is going to be, now, the junction law or rule. Okay, this states that the total current before a junction is equal to the total current after the junction. Okay, so at a junction, current could either, so at a junction, current either splits or converges. Okay, and it makes sense. Beat me in here. All right, so imagine we have these two scenarios. This is scenario one. We have current coming from this direction, okay, and it reaches a junction, okay. So at each and every junction, current will always split, but then it doesn't split into two equal parts. It splits according to other factors like what resistor you have on each side. So I'm going to call this current I1. This I1 will appear, or rather appears to be the main current. This current is going to split into two. One part to go this side, one part to go this side. I'll name this one I2, I'll name this one I3. Okay. The same would happen at this junction. We could have two currents approaching a junction. This is maybe I1, this is I2, approaching a junction. So this is splitting, you get, and then this is converging of current. So this is going to give us one current, which we're going to label as I3. So the rule is the total current before a junction is equal to the total current after. Okay, so the current before this junction is I1. So the formula for this, the junction law for this setup would be I1 is equal to these other two, I2 plus I3. And it's important that you remember this law because it's the easiest. The other one is a bit more challenging. For this other one, we have these two currents converging. So we're going to have I1 plus I2 is equal to I3. So it just depends on how you label them. I could have labeled this one to be I3. I could have labeled this one to be I1, this one I2. It doesn't matter as long as you add everything and equate it to the main one. You get? So current could either split or converge. So the first law is the junction law. I'll ask you these questions. So junction law, some books would say the junction rule. You get? So it's the same as long as you know how to use it. And at least if you can remember, if you know how to use it, obviously you'll be able to remember how to state it. The next one is the loop law or the loop rule. Number two, the loop law. Some people would say the loop rule. So we'll define what a complete loop is, okay? But for now, let's state the law. We're going to say the potential, some people would say the potential drops, the potential differences, so it doesn't matter. The potential differences in a loop should, the sum of the potential differences in a loop should add up to 0. Okay, so a loop is basically just a part of a circuit that is closed up. So we can say a loop is a part of a circuit that is complete. by itself. Okay, so you're going to see network ireshupa. Are you guys able to hear me? Can you see what I'm doing? Can you hear me? If you're able to hear me, just say okay. Are you guys able to hear me? Because we want to make sure everyone is following. Are you guys able to hear me? Can you get me clearly? Okay, good. So, what two laws do we have under Kirchhoff? So just state them. What two laws do we have? So that we make sure we are moving as one. What two laws do we have? What two laws do we have? So Kirchhoff has two laws. What laws are those? What are the two laws of Kirchhoff? Our network is really bad, because when I was starting this live session, it actually gave me an error. So hopefully you guys are able to get me. So yes, we have the current law. Current law is also known as the junction law and the loop law. You get? Yeah. So the current or the junction law is straightforward. Now, the loop law, that is where things start getting a bit rough. Okay. So the loop law states that the sum of the potential differences or potential drops in a loop should add up to 0. So what is a loop? A loop is a part of a circuit that is complete by itself. You get? So you can have one loop. For instance, you have a battery, you have a resistor. So this is sort of a complete flow of current. This is a loop. Or this can be connected to something else. And this alone can be said to be a loop. You get? So a loop is basically just a complete path where you start from somewhere, you go around, and you go back to where you started. Whatever path you take, that is going to be your loop. Now, a loop has two things. A loop has two things. Now, part A loop is going to have a resistor. So a resistor is anything that uses up some electricity. Loop law and Kirchhoff's law. Amayo awe. Chipasha. Loop law and the junction law. Okay, so a loop has two things, a resistor, and it's going to have a battery or cell or voltage source. Okay, battery, cell, voltage source. You know, a battery is when you have more than one cell. A cell is when you just have one voltage source. Just some anything that could push electrons in a wire. Okay, so a loop is going to have two things, a resistor or a battery, but we'll be using the word battery and cell interchangeably. Now, you need to know what happens when you reach a resistor, and you need to know what happens when you reach a cell. Remember I told you the loop law, that's where things get a bit challenging. So let me just give you a summary for those that have just joined us. So Kirchhoff's laws. Laws. Number one, we said we're going to have the junction law. Okay, the junction law, some people call it rule. Some people would also refer to the junction law as the current law, because obviously it talks about current. Okay, and this talks about splitting of current or converging of current. If this is I1, this is I2, this is I3, we're moving from here to here, current will split. We're going to say I1 is equal to I2 plus I3. Okay, The same current can converge here to give us that. If this was I1, this is I2, I3. So we're going to say I1 plus I2 is equal to I3. These are just subscripts. Just know that current could either converge, as is the case here, or it could split. Number 2, we have the loop law. Some people would still call it the rule. Okay, this says the potential drops in a loop should add up to 0. So potential differences in a loop should add up to 0. Then, what two things did we say we are going to meet in a loop? What two things did we say we are going to meet in a loop? What two things did we say we are going to meet in a loop? What two things did we say a loop is going to have? Excellent. So we're going to have resistors and a battery. We just use the word battery. Whether we're referring to one and so on, it doesn't matter. So we're going to have resistor and a battery. But of course, a battery is also called a cell. Okay, so there's a mnemonic that you're supposed to know for resistors, and there's a mnemonic that you are supposed to know for batteries or cells. And the mnemonic that you're supposed to know is resistors love opposition. Resistors love opposition. Very soon I'll ask for this mnemonic because this is what we're going to be using in our calculations. Resistors love opposition, or resistors love to be opposed. Okay. Then for the battery, the mnemonic that you are supposed to know is the last sign touched by the loop is the sign of the voltage drop. The last sign touched by the loop is the sign of the voltage drop. So these are very important mnemonics that you guys should know. For resistors, resistors love opposition. Okay? They love it when they are being opposed. For batteries, the last sign touched by the loop is the sign of the voltage drop. And then, by convention, we are going to take the shorter part to be negative, the taller part to be positive. So let's look at the loop rule in depth. We are going to look at resistors, the two possibilities. We're going to look at batteries, the two possibilities. Don't get confused. We're going to have the junction law and the loop law. The loop law can further be divided into two things based on what you're looking at. You can either look at resistors or batteries. Now, resistors are going to give us two scenarios. Batteries are going to give us two scenarios. At the end of the day, there are five things that you're supposed to know. The four scenarios under the loop law and the junction rule. Sharp. Know the four scenarios under the loop law and know the junction rule. Two of those scenarios under the loop law come from the resistor. Two of them come from the battery. And then the mnemonic that we use for resistors are, or rather is, resistors love to be opposed. The mnemonic that we're going to use for batteries. Vambi badeta epahamu dudu, bati kweye na. Ngamamu ibushoyo wakumuflira. All right. So, battery or cell. Then, as a convention, the taller one is going to be said to be the positive. The shorter one is going to be said to be the negative. Namwe examu, namwe muka kwate ama max kwati munenu hamu dudofu wale. All right. So let's look at the two possibilities under resistors. Let's look at the two possibilities under batteries or cells. I need you guys to really get the picture. Okay, so more on the loop law. So let's look at resistors. What mnemonic did we say we are going to use for resistors? What mnemonic did we say we are going to use for resistors? What mnemonic did we say we are going to use for resistors? What mnemonic did we say we are going to use for resistors? Good. Resistors love opposition. Okay, or resistors love to be opposed. That guy has actually gained some popularity because of his name, but he's a cool guy. He's a cool guy. Okay, so resistors love to be opposed. Resistors love to be opposed. Okay. Now, there are two scenarios. Oh, by the way, a resistor is denoted by a wavy line. So this is going to be a resistor. This is going to be a resistor. Okay? Now, two things are going to happen across a resistor. I need you guys to pay attention. Take a deep breath. Now, we have the junction law and we have the loop law. Loop law can be divided into two parts. The part that's talking about resistors and the part that's talking about batteries. The part that's talking about resistors, we're going to have two possibilities. The part that's talking about the battery, we're equally going to have two possibilities. Right now, we are talking about a battery, or rather a resistor. Okay, so two things can happen across a resistor. Okay, we can have a loop, and I'll explain to you what a loop really is. When we do a full question, you're going to understand. So a loop can either go in the clockwise direction, or a loop can be made to go in an anti-clockwise direction. It depends on what you want. Okay, so this is our loop. This is our loop. Okay, then across a resistor, we are going to have current flowing through. Now, the same way we can have, we don't know in which direction a loop would be chosen. We can have clockwise or anti-clockwise. It's the same way that we don't know the direction in which current could go. Current could choose to go to the right-hand side, or current could choose to go to the left-hand side. We don't know what will meet, but any one of these two is a possibility. You get? Any one of these two is a possibility. Now, let's take current to be going in one direction, and then the loops are what will change. Let's take current to be going in one direction, and then the loops are what to change. So, resistors. So resistors are shown by wavy lines. And then let's take one loop to be clockwise, one loop to be anti-clockwise. And in both scenarios, we are going to take current to be going in the same direction, going to the right-hand side. So these are the two scenarios that you're going to meet. In one scenario, we are having some opposition, and in one scenario, we are not having opposition. You get? So, the mnemonic was, resistors love to be opposed. Love to be opposed. Now, here, the loop, I need you guys to follow me properly. The loop is going in this direction. The current is also going in this direction. You get? At this point, the loop is going in this direction. The current is also going in this direction. Do you see any opposition here? Yes or no? Regarding the loop and the current, do you see any opposition? Or they are supporting each other? Do you see any opposition on this setup? The loop is going in this direction, the current is equally going in this direction. Do you see any opposition? There is no opposition. Okay. On this other setup, the current is going in this direction, but the loop is going in this other direction. Do you see opposition on this other one? The current is going in this direction for the second one, and the loop is going in the other direction. Do you see any opposition for the second one? For the second one, do you see any opposition? Current is going this side, the loop is going this side. Okay, so we said resistors love opposition. You understand? And we are talking about the loop rule. What does the loop rule state? What does the loop rule or law state? I need us to be together on this one. I need us to be together on this one. What does the loop law or rule state? What does the loop rule state? What does the loop rule state? Because if you understand, if you can pick up opposition, or you can pick up scenarios where there's no opposition, and you understand what the rule states, then things will be much, much easier. So potential difference in a loop should add up to 0. Now, can you give me anyone to give us the alternative name? Anyway, let's not waste time. The alternative name for potential difference is voltage. So potential difference, the alternative names could be EMF, electromotive force, or they could refer to it as voltage. These are the alternative names to potential difference. Okay? So yes, the potential differences in a loop should add up to 0. Now you need to know the alternative names for potential difference. The alternative names are electromotive force or voltage. You get? So the rule could also be stated to say the voltages should add up to 0, because voltage and potential difference, these are synonymous. You understand? Now, what is one equation that I gave you that connects voltage, resistance, and current that I gave you? What is one equation that I gave you when you just started? Even from grade 12, you should know this one. I even told you that just think of the word virus and you'll be able to remember this equation. What equation did I give you that connects voltage, resistance, current? V is equal to IR. So let's work together. We have said that the potential differences, the sum of potential differences in a loop should be equal to 0. Then we say the alternative name for potential difference is voltage. You understand? Voltage or electromotive force. We are going to stick to voltage. Then we say voltage has an equation, V is equal to IR. You understand? So, whenever a resistor is involved, the voltage across that resistor is gotten by multiplying the current passing through that resistor, current I, and the resistor R. When you multiply I by R, you get the voltage or the potential drop across this resistor. Now, potential drop could be negative or it could be positive, depending on whether the current and the loop are opposing each other. Relax. Relax. This lesson should have been held in the afternoon when people's minds are a bit more fresh. But don't worry, this could be like an introductory lesson. Okay. So let me start. In a loop, we are going to meet a battery. A battery is going to have voltage, obviously, okay? And in a loop, we are going to have resistors. You understand? Resistors are also going to have voltage. Because in a loop, for instance, we can have that. This is R1, this is R2, this is E. You get? And then this is positive, this is negative. So current is going to flow like this. And it will go back. Because this current is not splitting, I'll just call this current I. No need of saying I1, I2. You get? So there are three things. So one thing will provide the voltage, and then the resistors will eat up that voltage. So there's voltage here at a battery, and there's voltage in inverted commas across each resistor. It's like they're eating up some voltage. You get? The voltage from the battery is denoted by E. And obviously it is referring to the electromotive force. The voltage that is eaten up across a resistor, that voltage is equal to IR. So the voltage across a resistor is what we get when we multiply the current flowing through the resistor and the resistance of the resistor. You get? So the voltage across this one, V, is going to be IR1. The voltage across this one, V, is going to be IR2. So voltage can also be denoted by the letters I and R. So let's start. Potential difference is also known as voltage or electromotive force. You get? Electromotive force is just denoted by the letter E. Voltage has an equation that is V is equal to IR. So wherever I have voltage, I can put IR. Or whenever I have IR, it is representing voltage. Are you guys following? Are you guys following? Are you guys following? Are you guys following? Nambweke shape. A summary has never hurt. In a loop, we are going to have two things. We're going to have a battery, and a resistor. Voltage across a battery is denoted just by using an E. Okay? Voltage across a resistor can be denoted using V or IR. So the voltage across this resistor, I can denote it as V or I can denote it as IR because V is equal to IR. So whenever I put I times R, I am referring to voltage. Okay. Now, remember the scenarios that we had across a resistor. We said we are going to have a loop going in this direction. We are going to have a loop going in this direction, and current will be going in the same direction for both. This is going to be a resistor R. This is going to be a resistor R. Current I. Okay. What two letters would represent the voltage across this setup, across setup A? What two letters would represent the voltage across setup A? Instead of using letter V, what other two letters can I use? Okay, that would still represent letter V across this resistor. So whenever I put I and R, it is still representing V. So IR is the alternative name for voltage, or the alternative form for voltage. You get it? Good. We are getting it. Then we say resistors, because we're still talking about resistors. The mnemonic that we used was resistors love opposition. Okay? And if you look at these two setups, this is going to be setup A, this is going to be setup B. Between setup A and setup B, which one has opposition? Between setup A and setup B, which of these two has opposition? Between setup A and setup B, which of these two is going to have opposition, or rather has opposition according to the way that we have phrased it? Setup B is going to have opposition. You get? Now, if resistors love opposition, then they hate it when there's no opposition. Let me just write that. Then resistors hate it when there is no opposition. You can now think about Hamudud. So, if resistors love opposition, then they hate it when there is no opposition. When I use the word love here, and when I use the word hate here is going to represent a negative. And love, obviously, is going to represent a positive. Because when you hate something, then you're sad. You understand? And remember, we said sad goes with a negative sign. If you love something, then you're happy. Okay? And happy goes with a positive sign. Resistors love opposition. So wherever you see opposition, just know that the sign there for the voltage should be positive. Wherever you don't see opposition, just know that the sign there should be negative. So let me write that. If you see opposition, we're going to have a positive voltage. If you don't have opposition, then you're going to have a negative voltage. Okay. So, setup B, we can see opposition. Now, the voltage across setup B, we're going to say V is equal to. Now, because we have opposition here, is the sign for the voltage going to be positive or negative? Because we have opposition for setup B, is the sign for the voltage going to be positive or negative? Remember, resistors love opposition. And wherever you see opposition, just know, anyway, I don't want to preempt. Because there's opposition here, is the sign for the voltage going to be positive or negative? And I'm just from showing you this. If you see opposition, just know that the sign should be positive, okay? Resistors love opposition. So whenever you see opposition, just know that that voltage should be positive. So this is going to be positive IR. You get? Hamududu. Hamududu Hive. I actually thought that was a female, and when they said Hive, I thought Baresuna Ivy. So I thought it was a female. Anyway, Hamududu. Let's continue. All right, this voltage is going to be positive because we have opposition. Okay, this other voltage, we don't have opposition. You understand? So is this voltage going to be positive or negative? Because we don't have opposition. Is this going to be positive or negative? You're going to see how we're going to put all these things together. This other voltage is going to be negative, okay? We said if you don't have opposition, then the sign is going to be negative. So this is going to be negative IR. So voltage could be positive or negative across a resistor, depending on whether the loop and the current are opposing or not. If the loop is opposing the current, you're going to have positive voltage. If the loop is supporting the current, you're going to have negative voltage. So even as you sum up all the potential differences in a loop, some of them will be positive, some of them will be negative. Do you guys get that? We said the loop rule states that the sum of the potential differences in a loop should add up to 0. Okay? Now, we are going to add more to that. The potential differences can be positive or negative, okay, depending on what happens. If you're looking at a resistor, the potential difference or the voltage is going to be positive if the current and the loop are opposing. The potential difference across a resistor is going to be negative if across a resistor the current and the loop are supporting each other. Okay, easy stuff. Easy stuff. So once again, let's summarize. We're looking at Kirchhoff's laws. There are two laws of Kirchhoff. We have the junction rule and the loop rule. Okay, junction and loop. Then, junction, there are two possibilities. Across a junction, we talk about current time. Current is either splitting or converging. Okay. Loops. In a loop, what two things did we say we find in a loop? I need us to be together. Kirchhoff's laws, we're either talking about the junction rule or the loop rule. Okay. Junction rule, things are either, current is either splitting or converging. You get? Loop rule. What two things do we find in a loop? What two things did we say we are going to find in a loop? What two things did we say we are going to find in a loop? Resistor and battery. So let's talk about resistors. resistor and a battery. So resistor, across a resistor, we are trying to compare the loop and the current. Okay? If the loop and the current are opposing each other, the loop and the current could either be opposing each other or not opposing. Okay? If they are opposing each other, is the voltage going to be positive or is the voltage going to be negative? If the loop and the current are opposing each other, is the voltage going to be positive or is it going to be negative? Remember, resistors love opposition. Resistors love opposition. Okay, so this is going to be positive, and then voltage, the alternative, the thing that you can equate V to is I and R. I hope it's making sense. Next, if it's not opposing, obviously it's going to be negative I, R. Good. So the only thing that we now need to talk about is the battery. So Kirchhoff's laws can either have the junction rule or the loop rule. Okay? Junction rule, current is either splitting or converging. Loop rule, at a loop, in a loop, you either have a resistor or a battery. When we look at a resistor, we are trying to compare the directions of the loop and the directions of the current. If they're opposing each other, voltage is going to be positive. If they're not opposing each other, voltage is going to be negative. Okay. Now, let's go to batteries. Okay. What mnemonic did I give you for the battery? Anyway, let me just help you. We said the sign that is touched last. I may use different words, obviously. The sign that is touched last by the loop is the sign of the voltage. Okay. Do they always give the direction? No. Direction could either be given or you have to come up with your own. I'll show you both scenarios. Okay. I will show you both scenarios, so do not worry. So, the sign that is touched last by the loop, or the sign that the loop touches last, is the sign of the voltage. Okay? What do I mean? What do I mean? So this is a battery, the short one. What sign does the short one represent? What sign does the short one represent? Those of you that are not very tall, this is your chance to shine. What sign? Those that are short, they're going to correspond with the sign of the short one. So the short one actually represents a negative. Okay? The taller one represents a positive. Short one, negative, taller one, positive. We said there are two scenarios for a resistor, either opposing or not opposing. There are also two scenarios for a battery. Okay? The loop, imagine the loop is going in this direction. In this case, the loop is going in this direction. Let's follow this loop closely. Let's follow this loop closely. This loop starts, let's assume it starts here. Okay? We follow it. The first sign that what is the first sign that the loop will touch? What is the first sign that the loop will touch? What is the first sign that the loop will touch as we move along it? What is the first sign that the loop will touch? So the loop first touches a negative. Then it goes to the positive. You get? We said the sign that the loop touches last, that is the sign of the voltage. So it doesn't, like, don't really worry about the sign that is touched first. Worry about the sign that is touched last. In this case, the negative is touched first, and then the positive is touched last. Even if I go along, I go along the circle that would be formed, I'll still touch the positive first and the negative last. Or rather, the negative last and the positive. What am I saying? I'll touch the positive first. I will touch the negative first and then the positive last. Okay. All right. Yes. So I touch the negative first and then the positive here has been touched last. Okay? And I told you, voltage. What told I told you, voltage, we could represent it using the symbol IR, or we could actually represent it using the symbol E. We've talked about using IR and when we have a positive and when we have a negative. Okay? Now, we are now going to use an E. So for a battery, you always use an E. For a resistor, you always use IR. Okay? So here, the sign that is touched last is the sign of the voltage. So here, we touch negative first and then we touch positive last. Meaning this voltage is going to be positive. So this is going to be positive E. Okay. Here, this loop is an anticlockwise loop. Okay. We touch the positive first and then we touch the negative last. So this is going to be negative E. So you guys need to know the difference between a battery and a resistor. And the mnemonics will help you. For a resistor, resistors love opposition. For a battery, the sign that is touched last is the sign of the voltage. Okay? So, for resistors, if they are opposing, you get positive. If they are not opposing, you get a negative. Okay? Then for a battery, it depends on what sign is touched last. So sign touched last. So the two possibilities are, if we touch a positive sign, then obviously we're going to have positive E. If we touch a negative sign, then we're going to have negative E. So let me just separate these two things. So this is basically a summary of everything that you guys are supposed to know under Kirchhoff's laws. And if you don't know everything that I've talked about here, we can't handle a question. You get? So, Kirchhoff's laws, junction rule, loop rule. Okay, junction either splits or converges. Across a loop, we either have a resistor or a battery. For resistors, we look at the loop and the current. For batteries, we look at the sign that is touched last. For resistors, if the loop and the current are opposing, we get positive IR. If they're not opposing, we get negative IR. For a battery, we look at the sign that's touched last. If we touch the positive last, that is going to give us positive E. If we touch the negative last, that is going to give us negative E. Yeah, so we either have positive IR or negative IR in a loop, or positive E and negative E. Positive IR, negative IR. Positive E, negative E. You should know when we get positive IR when there's opposition. You should know when we get negative IR, no opposition. You should know when we get positive E, positive touched last. You should know when we get negative E, negative touched last. Okay. All right. I don't know if you guys are strong enough. I don't know if you guys are strong enough. I don't even know where my other phone is. Anyway, Yeah, so please meditate on everything that we have done. Then we are going to go live again to do a question. Right. We're going to do 3 exam questions on Kirchhoff's laws. And yeah, you guys, hopefully you're going to get everything else that we're going to talk about. So please just meditate on everything that we've done today. It's important to have an introductory lesson so that you guys actually become familiar with the material. Okay? It wouldn't be nice for me to introduce this much today and go very deep again. Okay? So for now, just meditate and think about it. Write your pointers and the like. Which one is the voltage rule? So voltage rule is the loop rule. Okay, because it's talking about the voltages. Then the junction rule is the current rule. What time? We'll most likely meet around maybe in the evening. Maybe around 18 or 19. I'll let you guys know. All right, have a good night. Please reflect on everything that we have done. At least we've managed to have this session. Everything kept pointing towards cancelling this lesson, but then no, we have to move. We are baby. All right, good night. Take care.